Welcome everybody, good to be with you again. Today's topic is going to be the Milky Way galaxy, but before we get started in that, tell me, what is at the center of all galaxies, as far as we can tell, and the key word here is all. Go to your Moodle clicker quiz to answer that question when you're done watching the video. So, what's our Milky Way like? We've talked about galaxies, the types of galaxies, spirals, ellipticals. We've talked about dark matter. So now we're going to zoom in on our galaxy just for a bit. This comes from chapter 25 of our OpenStax book. So some things we're going to talk about first is the shape of the Milky Way. So, oops, gotta put it on my pen. This is section 25.1. What type of galaxy is ours? What is the shape of the Milky Way? And you can see from this picture here, this is an artist's idea of what our Milky Way galaxy might look like if we were able to get out of it and look from above. It has a bar. We live in a barred galaxy. Substantial, which I can't spell very well. I'll figure this out. Here we go. Ooh, big eraser. Substantial bar and a modest bulge. So modest, medium-sized bulge. We didn't know that our galaxy had a bar for quite a while. That's a fairly recent idea. We have two major spiral arms and some little smaller things, but the two major spiral arms, and of course a flat disk. So you can see the major arms here, this one, the Sectum Centaurus, and the Perseus arm, with some smaller things in between. So there's our Milky Way, a giant barred spiral. But what we're going to talk about a little bit more today is what's going on outside of the disk. We actually have a halo of old stars and something that we call globular clusters. So a lot of this video is going to focus on globular clusters and what they can tell us about the history of our galaxy. So we have this halo, and you can see in the picture here, here's our disk, the bulge. Around the disk we have a halo, and this is a halo of old stars and globular clusters. So hopefully you're thinking, well, I thought we also had a dark matter halo, and that's exactly right. The dark matter halo is actually much, much larger than our globular cluster halo, because when we plot the rotation curve of the Milky Way, we see that it is flat, and it tells us that we have dark matter that extends way beyond any visible stars into a huge halo that extends beyond that other halo that I was just talking about. I know, they're both called halos. That's confusing. Dark matter halo extends beyond visible halo. Okay? And how do we know this? Because this is a plot of our rotation curve, that the Milky Way has a flat rotation curve. And we saw this in the lecture tutorial that you all completed. The Milky Way has a flat rotation curve. That means there is something out there that has mass, because if it has mass, it has gravity. Way out here, there's something with mass and gravity that is causing those stars to keep their speeds up high and not see a decrease. So, Milky Way, barred spiral, dark matter halo, and this interesting halo of globular clusters. So what in the world is a globular cluster and why are they important? Why do we care? Globular clusters is our next topic. Globular clusters in the halo. And this is just the regular halo, right? So we have definition to start us out. What is a globular cluster? It is a glob of stars. It is a large, spherical, so ball-shaped group of bound stars. They are all gravitationally bound together, and they were all formed at the same time. So this picture might look a little bit like an elliptical galaxy. It's similar, but much, much smaller. Elliptical galaxies might have billions and billions of stars. A globular cluster might have thousands, maybe 100,000, maybe 200,000, but not millions or billions. So a lot smaller, and they were all formed at the same time, which is something that you don't see in an elliptical galaxy. So a smaller glob of stars. These are really beautiful objects, and we can see some in our night sky with telescopes. So, why do we care? Well, it turns out that these globular clusters are actually the oldest part of our galaxy. And so, that's kind of an interesting thing. We want to know why and what can we learn from that. So they're the oldest part of our galaxy. They're almost as old as the universe. They can be about 13 billion years old. Best estimates for our age of the universe, which we'll get to later in the semester, are around 13.5 billion years old. So these are some old stars. That means that they formed very early in the universe. They're some of the first things that formed. So how did they get to be part of our galaxy? Well, we're going to build up to that. We're going to learn a little bit more about these globular clusters and then talk about how galaxies formed, we think. Okay. So how do we know that they're old? Well, just like we saw, sorry, I'm having technical difficulties here. Just like we saw with the elliptical galaxies, we know these guys are old because there are no young stars present. All of the high mass stars have died. And so I'm going to take you back to the HR diagram here real quick. You see these HR diagrams over here on your screen. Notice, look at the top of the main sequence. There are no high mass stars left. You see some have evolved off the main sequence. Some of these high mass stars are now supergiants. Remember, not all supergiants are red, but they sort of go back and forth here. And then we have down here, we have, we have the rest of the main sequence, and we have our red giant branch, and horizontal branch and AGB branch, all of that good stuff here. Okay, so no high mass stars. They would actually be really high up here. We just see low mass stars and giants. So, what else do we know about these guys? Well, they are luminous because you get 100, having trouble today. You get 100,000 stars or 200,000 stars together, and they're pretty bright. So they're luminous. And so we can see them, we can study them from where we are in the Milky Way. So can be seen from far away, because a lot of them are far away from us. And the cool thing is that because we can see them, we can map them, and we can know what the distances are to them. So they can actually help us map out the Milky Way, can help find distances. In the Milky Way, because they contain special stars that we call standard candles. Because they contain stars that are standard candles. Okay, standard candle, that's kind of an interesting thing here. Standard candles are stars that are always the same brightness. It turns out that these are actually stars that change their brightness. They get brighter and dimmer. And because they get brighter and dimmer on a regular basis, we know exactly how bright they are. So can help find distances in the Milky Way because they contain stars that are standard candles. Sorry, I forgot that S. What is a standard candle? A standard candle is a star. I was writing down there. Standard candle is a star with a known brightness. Not my best video today, y'all. Bear with me. Not sure what my problem is today. A standard candle is a star with a known brightness. It wants to keep writing down there, and that's just really strange. So we know its distance. Alright, that is some ugly handwriting, but hopefully you can read it. Let me read it again. A standard candle is a star with a known brightness, so we can know its distance. That goes back to talking about the HR diagram and what we know about luminosities, and I just sort of want you to get the main idea. If it's a standard candle, it's easy to find distance. These globular clusters have standard candles, so we can map them. We can figure out their distances. This was actually used about 100 years ago to map out the Milky Way, and at that time we figured out that all the globular clusters that are in the halo are part of our galaxy because they orbit around our bulge, or around the center of the Milky Way. I'm going to abbreviate Milky Way. Handwriting's bad anyway. Okay. So we actually used these globular clusters after we mapped them out with their known distances from standard candles. We used them to figure out where the center of the bulge was. We didn't know that 100 years ago. This is how we figured it out. So we used globular clusters to find where the center is. And we found out, where is it? It's about 25,000 light years from us, from the sun. 25,000 light years from the sun. So that's what this picture is showing here. Here's the galactic center right here, this little dot. Here's the sun over here. All these pink things are globular clusters, and we were able to figure out how far they were and how they were moving, and we found they're all moving around, they're orbiting around